Alright, in this example problem we're going to use Castigliano's method to determine the deflection at the mid-span of our simply supported beam. The stiffness of the beam is just, we can just treat as being equal to E to IZ, and we're going to ignore the effects of shear force on the strain energy in the beam. So the first thing we need to do for this problem is we're going to take the boundary conditions at A and B where we have a pin and a roller connection, and we're going to replace them with reaction forces RA and RB. There would be a reaction in the x direction also for this pin, but there's no forces in the x direction, so we can set this equal to 0. The other thing we're going to do is we're going to apply a fake or a dummy load Q, which is equal to 0, but we need to apply this load in order to determine our deflection at that point. So if we do our so if we use statics, what we can do is we can sum all of our sum all the moments about point B and set it equal to 0. If we do that, we'll get W times the length of the beam times length over 2. That'll create a positive or counterclockwise moment. We'll also have a positive moment due to Q times length over 2, and then we'll have a negative moment due to RA times the length. Alright, so if we move RA to the other side and divide it by a length, we'll get that RA is going to be equal to WL over 2 plus Q over 2. Alright, so if we wanted to, we could also sum all of our forces in the y direction and set that equal to 0 to solve for RB. So if we did that, we'd end up getting that RA would be equal to, since it's symmetrical, RA would be equal to RB. Okay, which would be so. Anyhow, all right. So for what we can now do is we're going to take a section cut, between I'll call this point C, between point A and point C. So so this is going to be between x, when x is between 0 and L over 2. What our section cut looks like is we'll have RA. Alright, and then we'll have our shear force at our section cut, we'll have our couple moment at our section cut, and we'll have our distributed load W applied to the system. Okay, so if we do all this, what we're going to end up getting is we're going to get that the moment at the boundary, if we sum all of our moments about the section cut, it would be equal to 0. So if we do that, we'll end up getting M of Z, which is the moment at the section, minus RA times X plus W times X over 2. Alright, so what we end up getting is that M of Z is going to be equal to RAX minus WX squared over 2. We're going to plug in the value for RA into this equation, so we'll get M of Z is going to equal to WL over 2 plus Q over 2 times X plus WX squared over 2. So we'll end up getting that M of Z is going to be equal to Q over 2X plus W over 2 times WX over 2 times L minus X. Or L, sorry, that should be L minus x. All right. Yeah. Okay. So so for the second part of the problem, we had to take our suction cut from L over 2 to L. So what this looks like is we still have our reaction force at A. We still have our moment, or sorry, our distributed load W. Alright, we have the addition of our concentrated load Q. Alright, and we're going to solve for our couple moment at our internal force here. Alright, so if we sum all of our moments about at x, or at our section cut, what we'll end up getting is we'll get, and set that equal to 0, we'll get mz plus w times x over 2 minus plus q over times x minus L over 2. Alright, and then we'll have a negative moment due to the reaction at A. Alright, if we plug all this in, we'll end up getting that mz is going to be equal to Ra times x plus w x times x over 2 plus q times x minus L over 2. So this is the same equation except for the additional q component, so we can simplify it down. If we plug in what we know of Ra is equal to, what we get for mz of x is we'll get q over 2 x plus wx over 2 times L minus x minus q times x minus L over 2. I should say plus. Alright. So since these two were the same as before, and I'm sorry, this should be negative, not positive here. And this should be negative as well. Oops. Alright. So since we have symmetric loading, we can simplify this problem and we can integrate from 0 to L over 2 and then multiply that integral by 2 instead of doing two integrals from 0 to L over 2 and from L over 2 to 2. So if we do that, what we'll end up getting for our integral is, using Castigliano's theorem, we say delta C is going to be the displacement at point C is going to be equal to the partial derivative of the strain energy U with respect to our dummy load. In this case, that dummy load is Q. If we multiply, so our integral will be from 2 times L over 2, 1 over e to the iz, so this is the simplified Castigliano's method, times mz of x times d mz of x with respect to q dx. Okay, so if we plug in our mz of x function and our dmz x dq function, so we plugged in those two values from the last page, and at this point we can now set q equal to 0 in our problem. So our integral will simplify down a little bit, and it'll end up being equal to 1 over e to the iz times wx over 2 times L minus x times x over 2 dx. Alright, so if we simplify this integral down a little bit more, what we'll end up getting is we get 2 over the 2 here and the 2 here will cancel out. We'll bring out the e and the iz term here, and we'll be left with just 0 from L over 2. We'll have w x squared over 2 wx squared over 2 times L minus x dx. Okay, so if we do this integral, what we'll end up getting is we get 1 over 2 e to the iz times from 0, and we'll get, and we can bring out the w as well, and then we'll be left with L x cubed over 3 minus x x to the 4th over 4 from L over 2 to 0. Okay, so if we evaluate the bounds of our integral, what we'll end up getting is we get w over 2 e to the iz times the length over 3 times L over 2 cubed, which would be the length cubed over 8, minus 1/4 times the length over 2 to the 4th, which would be the length 4th times 16. Okay, so what we end up getting here is we get WL to the 4th over 2 e to the iz times 1 over 24 minus 1 over 64. The least common denominator for both of these is 192. So we get L over 4 2 e to the iz is going to be equal to 8 minus 3 over 192, right? Which ends up being 5 WL to the 4th over 384 e to the iz, which is our solution for the displacement at delta C. Okay, so just to recap the problem, the major steps of the problem. The first thing we need to do is we use statics. So we use statics to solve for our reactions. Alright, in terms of the applied forces. Alright, the second thing we did is that we calculated our moment as a function of x. Alright, once we had mz of x and we had our reactions in terms of our applied forces, the last step was we had to substitute mz of x into our equation here for our simplified Castigliano's method equation, and then the rest of the equation is I guess is like once we plugged it in to the simplified method, we could then set our dummy load equal to 0, and then the last step is just we had to just do the integration. Alright. So as long as you follow that general procedure of you should be able to solve these Castigliano's method problems. The integrations can be sometimes be a little bit long, but overall it's just being able to define your moment as a function of x, and once you can do that, you just have to do your integral. It's not too bad.